Now we are seeing a problem on principal stresses and strains. Let us see the problem. A point in a strained material is subjected to the stresses as shown in the figure. Locate the principal planes and evaluate the principal stresses. So this diagram is showing two perpendicular planes at a point in a strained material. So on these planes, the stresses are acting like this. And if you see in the y direction, 40 Newton per mm square tensile stress acting, and on this plane, suppose if you take this plane as a BC, so on this plane, stress is acting at some angle with this plane and this plane also. So that is given 60 degrees here, and it is like 60 in this direction and 60 like this in this direction given, and the value of this inclined stress with respect to this plane is 60 Newton per mm square. So here in this given case, we have to find out the value of principal stresses at this point, and also location of the principal planes at this point. So here first of all, so with for this case, first of all we'll resolve this inclined stress on this plane, uh, and this stress to the two perpendicular components. One is perpendicular to the plane BC and one is along the BC. When you resolve that, so after that we can simplify by using the formulas, principal stress formulas, major minor principal stress formulas, and also we'll use the condition for locating the principal planes formula. From that we locate the principal planes. So here, so I told, so we'll resolve this. This is not normal, so we'll resolve this for stress into normal component and tangential component with respect to this plane BC, and we'll find out the values of principal stresses by using the formulas available. So friends, before that, if you are new to my channel, please subscribe and also activate bell symbol for more videos and updates, and also please share my videos with your friends. So here, as I told, first of all we have to find out normal and uh, sh- uh, normal stress, and we have to resolve this given inclined stress perpendicular, and we have to resolve it to two components. When you resolve, you get one component perpendicular to this BC and one component along with BC, and also when you take this in this direction, so once again you will get one perpendicular component, one component along this AD. So any on my any one plane you can find out. So here just when you resolve this inclined stress which is given at 60 degrees with this BC in this direction. So when you resolve, so this component is perpendicular component, and this will become sine component, and this will become cos component because it is adjacent. We know that it's a cos component. So the value of this stress is given 60. So and angle is 60. So such that you will get here this perpendicular component as 60 sine 60. So the stress normal to the face BC or AD is nothing but 60 sine 60. We know sine 60, it is a 0.866, and if you simplify this, we are getting this value as 51.96 Newton per mm square. So this is the stress which is perpendicular when you resolve this. So this is a perpendicular component, and this is going in x direction. So this value is 51.96 we got. And also when you resolve this stress along this BC or AD, so this we can write it as it's a cos component 60 cos 60, and cos 60 we know it is 1 by 2 or 0.5. So when you simplify that, we are getting this as a 30 Newton per mm square. So but when you see this is given like this inclined inclination like this in this direction. So when you resolve into two components, one component is going x direction towards right, and like this one component we got anyway, another component along this BC it is going upwards. So this component of stress will create a shear action. So this component we can treat as shear stress. So on this plane, and if you see one in other direction AD is given like this. So when you resolve, one component you will get like this, and other component of the stress will go downwards. So anyway it is going upwards, and here it is going downwards. When you resolve that, you will get, so that value is 13 per mm square. So but in our theory part of this case 4, so this comes under case 4. So we have taken shear stress on this planes. So if you consider this side or this plane BC. So if it is going downwards at this plane, we are taking it as a positive shear stress. Or simply if you see along these two planes, if it is going clockwise, we are taking that shear stress as positive, but it is going opposite direction. So for with respect to our consider theory case, so this shear stress we have to take it as a negative. So anyway, the perpendicular component we got 51.96. So here it will go like this. So it will go like so. This we are taking this as sigma x and this as sigma y, and shear stress it is going anti-clockwise direction with respect to these two planes. So we know a shear stress is always accompanied with an equal shear stress in the planes right angle. So you'll get shear stress on these planes like this. So that will go clockwise. It is going anti-clockwise. So that other combined shear stress will go clockwise. So that is also same value, that is 30 Newton per mm square. So anyway, this shear stress is negative, we have to take. So here we are taking this as a major tensile stress sigma x 51.96, and this as a minor tensile stress sigma y 40 Newton per mm square, and shear stress on this two perpendicular planes as a tau, and that is minus 30 Newton per mm square. So here let theta is the angle at angle which one of the principal planes make with the stress 40 Newton per mm square. So here we are just assuming theta is a value of any one of the principal stress making with this 40 Newton per mm square some angle, means that is a one of the major principal stress location with respect to this 40 that we are assuming. And so from that, when you want the location of principal stress, so the condition is given by this formula tan 2 theta is 2 tau by sigma x minus sigma y. So this we have discussed in our discussion or derivation of case 4 on principal stresses and strains. So you can refer that previous video. So this is a condition to locate the principal planes. So that is 2 tau by sigma x minus sigma y. So 2 into tau value here is it's a minus 30. So when you substitute minus 30, and that is a 51.96 sigma x, and 40 is a sigma y. So when you substitute and simplify this value, we are getting minus 4.999, or 2 theta is equals to tan inverse of minus 4.999. So for this we have two values for theta will get. So one is minus 78.42 and one is minus 258.42. So those are two values for 2 theta, or you can say have two values for theta, that is theta 1 and theta 2. So for theta 1 the value will be minus 39.21 degrees, or and theta 2 will be minus 129.21 degrees. So here we got theta values minus, means see general case of case 4, that is when a point or when a body is subjected to two direct stresses, and also with a simple shear stress and oblique plane if you consider in that case. So that oblique plane is making an angle of theta with this cross section or with this BC in this direction. Means suppose when you start from here, it is a clockwise direction we have counted or we have taken. So by taking this condition, or by taking angle in this direction, in the clockwise direction with this BC or normal cross section, so we have derived the formulas, and we have taken the condition also, this condition. So this condition is this formula we got by assuming like this theta, we are assuming in this direction with this BC. So but we got minus, means we have that theta is in the opposite direction we have to measure. So that is a value meaning of minus. So when you take that in the opposite direction, or when you measure in anti-clockwise direction, because here this is the clockwise direction, so you got minus, means you have to measure with respect to BC, you have to measure anti-clockwise direction. So theta we got minus 39.1, means so with respect to BC, so when you measure theta 1 value in the anti-clockwise direction, so this is the location of one of the principal planes. So that is nothing but major principal plane you get for theta 1. So that is theta 1 value is minus 39, means so anyway you have taken for minus, you have taken in anti-clockwise direction. So simply you can write here theta 1 is 39.21 degrees. So this is the one of the principal plane, that is a major principal plane location with respect to this BC in this direction. So here on this plane, or plane parallel to this plane, you will get sigma 1, the major principal stress location, and the theta 2 value we got minus 129.21. So Once again, with respect to BC, how to measure in anti-clockwise direction. So 129.21 degrees. So this is the plane of minor principal stress. So these are the locations of principal planes. And also here we have to find out the magnitude of principal planes. So for that magnitude, we have formulas. Sigma 1 is equals to, and major principal stress, we are taking it as sigma 1 as a notation. So the formulas are sigma x plus sigma y by 2 plus under root of sigma x minus sigma y by 2 whole square plus tau square, the formula for major principal stress. And for minor principal stress, we are taking sigma 2 as symbol, and the formula is sigma x plus sigma y by 2 minus under root of sigma x minus sigma y by 2 whole square plus tau square. So these are the two formulas for major and minor principal stresses. So if you require derivation of these two formulas, please refer my previous video on principal stresses and strains, that is case 4. So anyway, to calculate the magnitude of major principal stress, so we are using this formula, and in this formula let us substitute these values. Sigma x we have taken it as 51.96 and sigma y 40 by 2 plus, and once again sigma x and sigma y values, and tau value we are taking our we got it is 30, and it is a negative, so it is minus 30 in the place of tau. So when you simplify that, when we are getting it is a 45.98 in the first term, and for the second term it is 30.6. So once again when you simplify that, we are getting the value for major principal stress as 76.58 Newton per mm square. And we have seen minor principal stress formula, and in this formula when you substitute the sigma x and sigma y values, that is sigma x 51.96, sigma y 40, and here also sigma x and sigma y values, and tau values as tau value as minus 30. So when you simplify, the first term is 45.98, and here the second term is 30.6. So when once again simplify that, we are getting sigma 2, that is minor principal stress value, as 15.38 Newton per mm square. So friends, this is the way to solve this kind of question. For more videos, please subscribe and activate bell symbol, and also please share my videos with your friends. Thanks for watching.